Hey, Alex Miss Johnson. Welcome back to another episode of Learning Calculus. Um, this afternoon, we're going to introduce the concept of a power rule for integrals, right? This is the first time we've heard of it, so be patient with yourself. It's a lot to think about. We're going to practice it for the assignment, and then we're probably going to talk about it again on Tuesday. So that's the plan. I'm going to take us through a trip backwards, talking about the Unit 2 derivatives. Connect it to Unit 3, we're going to make a power rule, and then we're going to practice it. And then your assignment is going to be practicing it, right? So here's what's going down. For Unit 2, we took the derivative. We learned how to do the power rule for derivatives, which was, here's some examples. We had, there's a function 3x, its derivative is 3. If their function is x squared, your derivative is 2x. If your function is 5x to the fourth, your derivative is 20x to the third. And the general rule that this follows is if your function is a number times x to the power of something, your derivative always is the coefficient times the exponent times x to the power of the exponent knocked down by 1, right? And this, n can be a negative number, n can be a fraction, n can be a decimal, right? Just if we have this pattern where it's number times x to the power of number, we get the derivative for free, basically. Not for free, we did a lot of hard work to get there. But we're about to get a similar rule for integration. And this is for indefinite integrals. Indefinite. At the moment, this is for indefinite integrals, right? This is the one where when you take the indefinite integral, you get an area function. Your answer should be like a function rather than just a number. Sometimes it's just a number, but here we are. So we talked about this in the first lesson for integrals, but integrating is the verb when you take a function and you move to the integral. And it is the exact inverse of derivative, right? So integrating something and then taking the derivative, it gets you back to where you start. Or taking the derivative and then integrating gets you back to where you start. So I've used the same examples, whereas if our function was 3 and we integrated, the integral of 3 is 3x. And this is, again, you might notice, the exact opposite of this process. So if we integrate 2x, what should we expect? Pause for dramatic effect. We should expect x squared. Looking at this, we integrate 20x to the third, we should expect 5x to the fourth. And in a more abstract sense, if we integrate something that looks like a times n times x to the power of n minus 1, we should get a times x to the n. We could stop here and use this as our power rule for integrals, right? It's generic. It says what we wanted to say. But to be honest, one of the nice parts of having it like this for the derivative power rule was it's just anytime we've got a number and an exponent, we know what our a is immediately and we know what our n is immediately. Whereas if this was our power rule for integrals, we would say if we had something like 7x to the 10, we'd have to say, okay, well, n must be 11 because this is 11 minus 1. And then if n is 11, 7 is a times n, so it's a times 11, so a is 7/11ths, right? And that's a nightmare. To have to do a bunch of pre-work to figure out what a and n are, and then to do this other thing, right? I would much rather have a formula where my initial condition is easy or straightforward, and my my conclusion is a little bit messy, right? So we're looking to have this be our if statement, and then our then statement be kind of confusing, because at this point we'll have nice numbers we can just plug in. So let's come up with the plan here, right? What is the power rule for integrals? If we say that this is true, let's just check this out. It looks like we're adding a degree for x every time. Right here we started with 0 x's, and we ended up with 1. Here we started with 1x, and we ended up with 2. Here we started with 3 x's, and we ended up with 4. So our power rule should be something something, right, times x to the n plus 1. So far, I think this makes sense. Here we went down. Here we're going to go up. It's an inverse operation. And then here, let's look at the coefficient. We had a 3, it stayed 3. We had a 2, it turned into 1. We had a 20, it turned into 5. It looks like we're dividing this first number by what our exponent will eventually be. Let me say that again. 3 divided by 1 is 3. 2 divided by 2 is 1. 20 divided by 4 is 5. So we're expecting, let me take all this off because notes will look better. So we're expecting this to be this number divided by this number. So a divided by n plus 1. The original coefficient divided by your new exponent. And this is going to be our power rule for integrals. We're going to say if our function looks like this, then our integral looks like this. And then to be a mathematician, to be super obnoxious, I'm going to say also n can't be -1. Because if n is -1 in this sentence, then this becomes 0 and we all fall apart. But other than that, it just always works. And then I'm going to write a side note. The integral of ax to the n is this, is another way to write this, right? And what you're doing, you divide the original coefficient a by the new exponent, n plus 1. So I just wanted to write that out in English because sometimes that's easier to read than in math. So now we've got our power rule. We've got our power rule for integrals. I'm going to talk about a little bit on Monday why I have a star here. But for right now, we're good. Let's do some examples. I'm going to write it like this. So we have our rule right up here. All right, so if we have, what's the integral of, let's start down here actually. What's the integral of 12x cubed dx? We say 12 is our a, 3 is our n. So our final thing will be 12 divided by 3 plus 1 times x to the power of 3 plus 1, which means 12 fourths times x to the fourth, which is 3x to the fourth. Bada bing, right? We can check our work. We can check our work for integrals by taking the derivative. If we took the derivative of this, we would say it's 3 times 4, and then knock the exponent down by 1, and lo and behold, we got our original equation, so we are right. That's our check. All right, let's do this next one. Let's do blue. I'm going to write in the exponent here just because it makes it nicer to say a is 6 and n is 1. That means our derivative is 6 divided by 1 plus 1, x to the 1 plus 1. That's 6 over 2 squared, which is 3 squared. I'm showing this work because I like showing work. I think that just writing this is showing enough work, because this is something that eventually we'll be able to do in our heads. Pretty straightforward. Let's check. If our function is this, our derivative would be this, because we're multiplying these two numbers and then knocking this down by 1, and we're good. That is, again, our original function. All right. Here's another example. I should have written these in backwards order. That's my bad. I'm going to write in that 4 is the same as 4x to the 0. So that when I take the derivative, when I take the integral, I can fill in my pattern where 4 is a and 0 is n. So I get 4x. Nice. Let's check. The derivative of 4x is 4. We're looking good. Let me copy and paste this and bring it along for the ride. Because we've got some more examples. Let me put it in a box. Boom. All right. Here, if we've got 13x, that means 1 is n, 13 is a. The integral is 13 over 1 plus 1 times x to the 1 plus 1. That's 13 over 2 x squared, and that is 6.5 times x squared. It's a decimal. That's totally fine. We should be confident with this answer. Great. And then if we want to, we were talking this morning about when you add up functions, it's the same as doing the integral of this minus the integral of this plus the integral of this. So it's working as we expected, or as we want it to, where we can just do all this at one time. So the integral of 7x squared, we'd say that's 7/3 x cubed. Did that kind of fast, but here's why. I write my original coefficient, divide it by my new exponent, knowing that my new exponent is 1 more than what we had. Let's do it again. This is 5/2 x squared minus 5x squared. Again, original coefficient. New exponent is 2 because the old exponent was 1. And then we divide by the new exponent. Here, I'm going to write this as x to 0. But also, straight up, I'm just going to memorize that whenever I've got a constant, I just add an x on the back. Right? There's going to be a couple of these, especially with the constants, that we're just going to kind of know. I'm not going to do this pattern every time for the constant one. All right, that is the power rule for integrals, y'all. I would add this to our note sheet that we made in class on December 4th, and that was this morning. And then, yeah, try out the assignment. Let's give it our best.